Hi, my name is Hanna, master student at the University of Quebec in Montreal under the supervision of Professor Benoit Marsan. Today I'll be presenting you my poster which resumes this year's work. So the project is the study of the copper, indium, aluminium disulfide semiconducting particles for homojunction solar cells. In the first place, I'm going to present you the CIS, which is the copper indium disulfide. The CIS is a promising ternary compound for photovoltaic application. It has a favorable bandgap energy value of 1.5 electron volts, which matches closely the solar spectrum. Plus, it has a high absorption coefficient of 10 to the 5 centimeters minus 1 that allows for greater than 99% of the incident photon to be absorbed within the first micron of the film. It's also possible to synthesize an N-type and a P-type semiconductor. However, we have a little problem. Indium is rare and expensive, so its partial substitution with another element with similar properties but cheaper is of great significance. So we have here represent aluminium as a substitution. So the two main objectives of the present work are the development of a protocol to synthesize the CIAS nanoparticles based on the CIS colloidal method. Then we have the study of the structural, optical, electrochemical, and electrical properties of CIAS materials with different aluminum content. So we have 0, 5, 10, and 50%. First, the colloidal synthesis is basically it's very easy and simple. So we have three solutions here. The solution of lithium sulfide, indium chloride, and aluminum chloride. We form a binary mixture with indium and aluminum, and then we add these binary mixtures to the suspension of lithium disulfide, and then we form the CIS particles. So after adding the copper source, and then we heat for 12 hours at 100 degrees. We filter, wash, dry, and grind, and then anneal at 700 degrees for 3 hours under vacuum. Then we have two methods of film preparation. First, we have direct deposition, is where we use a pipette and then just spread the ink on the ITO. The ink is formed with PVDF NMP solution, and then we add our CIAS. Then we dry in an oven for 24 hours at 40 degrees. The second method is collaboration with another laboratory. They have their aerosol jet printing instrument. So with an ink, they vaporize it on the ITO. It produces a film of 1 micron in comparison with ours that is 10 to 15 microns. So it's a big difference. First, for the results, for the X-ray diffraction here, we can see that there are three main peaks. They correspond to the chalcopyrite phase of the CIS. So when we add aluminium here, so this is 0, 5, 10, 20, and 50%. So as much as we add aluminium, the crystallinity increases, so the crystallite size increases as well. Here with the 10 images, we just confirm the crystallite size that we got from the XRD, and it matches very well. For the UV visible spectroscopy, we can see that when we add aluminum, the bandgap energy values increases, but non-linearly. We have to take into account that the CuAl-S2 has a bandgap energy value of 3.5 electron volts. So it's kind of logic to say that the bandgap has to increase with the aluminum. Then for the electrochemical analysis, we can see here that we did some VCs and some impedance spectroscopy. First, with the VCs of the different compositions of aluminium, we don't see much difference between them. This was made in a solution containing the redox couple, which is T2 and HC, in acetonitrile. The counter electrode was for the impedance spectroscopy. We confirmed first that it was an N-type semiconductivity, and the films showed that the partial substitution of indium for aluminium leads to a beneficial decrease in the charge carrier density. as much as we add aluminum, the density, the charge carrier density decreases. So from 10 to 19 to 10 to 18, which is a big difference. For the flat band potential, we don't see any trend with the aluminum content, so we can't say much about this. So as a conclusion, the partial substitution of indium for aluminum in the CIS structure leads to three different and major points: a higher material crystallinity and a lower value of charge carrier density, as we just said, both decreasing the device electron-hole pair recombination process. Second, the formation of semi-spherical nanoparticles with a slightly larger diameter, so 20 to 30 nanometers, and then a slightly larger semiconductor band gap energy value, so as we saw earlier with the UV visible spectroscopy. So that's pretty much it. Thank you.